A 7-mile wide visitor from another star system just smashed through our solar neighborhood at 137,000 miles per hour, carrying chemistry that should not exist in nature. 3I-ATLAS is rewriting the rules about what roams between the stars. You'll discover a comet that breathes carbon dioxide instead of water, bleeds nickel without iron, and survived longer than most galaxies have existed. If you enjoy unraveling cosmic mysteries that challenge everything we thought we knew about space, hit that like button. Prepare yourselves. We begin. 3I-ATLAS appeared on our telescopes like a cosmic missile, moving faster than anything natural should move. At 7 miles across, this interstellar wanderer dwarfs every space visitor we have ever encountered. Think of it this way. If the famous Oumuamua was a grain of rice, 3I-ATLAS would be a bowling ball. The size difference is so extreme that astronomers calculated we should discover 10 million smaller objects before finding one this massive. Yet here it sits, defying every statistical model we have built about what travels between stars. The speed tells an even more dramatic story. 3I-ATLAS races through space at 58 kilometers per second, carrying what scientists call hyperbolic excess velocity. This technical term hides a violent truth. Something catastrophic launched this mountain-sized chunk of ice and rock from its home system with enough force to escape not just planetary gravity, but the entire gravitational embrace of its parent star. What kind of cosmic disaster creates such velocity? Picture giant planets dancing too close to each other, their gravitational fields becoming weapons that hurl smaller objects into the void. Or imagine a dying star swelling to enormous size, its expanding atmosphere creating pressure waves that blast comets into interstellar darkness. 3I-ATLAS bears the scars of such violence, frozen in its trajectory for billions of years. The discovery itself reads like science fiction. ATLAS telescopes in Chile scan the entire sky multiple times each night, using artificial intelligence to spot moving dots against the static background of distant stars. On July 1st, 2025, machine learning algorithms flagged an unusual object. Within hours, observatories across the globe swung their instruments toward this cosmic intruder. The initial measurements shocked everyone. 3I-ATLAS follows what astronomers call a hyperbolic orbit, with an eccentricity of 6.141. In simple terms, it approaches our sun once and never returns. The mathematics revealed something even stranger. This visitor approaches from a direction that aligns almost perfectly with our solar system's equatorial plane. The probability of such alignment happening by random chance? Less than 0.2%. Professional astronomers began whispering about statistical impossibilities. Objects this large, moving this fast, arriving from this direction, should not exist according to our models of how comets get ejected from stellar systems. 3I-ATLAS had announced itself as an anomaly that would challenge fundamental assumptions about the space between stars. However, the real surprises were only beginning to emerge from the darkness. 3I-ATLAS carries the fingerprint of cosmic violence in its impossible speed. When astronomers measured 58 kilometers per second of hyperbolic excess velocity, they realized they were looking at something that had experienced traumatic ejection from its birth system. This speed represents pure kinetic energy, the mathematical signature of an object that escaped not just planetary gravity, but broke free from its parent star entirely. Think of it like a bullet fired so hard it not only leaves the gun, but escapes Earth's gravity and flies into space forever. The physics behind such velocity reveals catastrophic scenarios. Computer simulations show that achieving this speed requires gravitational encounters with objects at least as massive as Jupiter. Picture 3I-ATLAS as a smaller body orbiting peacefully in some distant solar system billions of years ago. Then massive planets begin migrating inward, their gravitational fields creating chaos in the outer regions where comets and asteroids reside. During these cosmic billiard games, smaller objects get flung around like marbles. Most crash into planets or get ejected at modest speeds. But occasionally, the gravitational mathematics align perfectly to create what scientists call a gravitational slingshot effect. The object gets accelerated to tremendous velocity, enough to break free from its stellar system entirely and begin a billion-year journey through interstellar space. Alternative scenarios paint even more dramatic pictures. Imagine 3I-ATLAS forming around a binary star system where two suns orbit each other. As these stellar companions age, one might expand into a red giant, disrupting the delicate gravitational balance. The expanding stellar atmosphere creates pressure waves and radiation that can blast smaller objects into the void with tremendous force. Even more extreme possibilities involve stellar encounters. Our galaxy contains over 100 billion stars, all orbiting the galactic center in complex patterns. Occasionally, two star systems pass close enough for their gravitational fields to interact. During such encounters, smaller bodies in the outer regions of both systems can get ejected at tremendous speeds. Launched into the space between stars like cosmic refugees, the speed of 3I-ATLAS also reveals something profound about time and distance. At 58 kilometers per second, this object has been traveling through interstellar space for potentially billions of years. It has survived the harsh radiation environment between stars, where cosmic rays strip away surface materials and solar winds from distant stars create a hostile environment that destroys smaller objects. Yet 3I-ATLAS endured this journey intact, its internal structure preserved like a time capsule from an ancient stellar system. The chemistry locked inside its nucleus represents conditions that existed when our galaxy was younger, when different types of stars dominated the cosmic landscape and planetary formation followed different rules than we observe today. The mathematics of its trajectory suggest 3I-ATLAS originated from somewhere in the galactic thick disk, a population of ancient stars formed when the Milky Way was still young and chaotic. These stellar systems contain lower concentrations of heavy elements compared to our Sun, suggesting 3I-ATLAS formed under conditions dramatically different from anything in our solar neighborhood. But the real mystery lies in how our artificial intelligence systems managed to catch this cosmic bullet at all. 3I-ATLAS should have remained invisible forever, but artificial intelligence caught it in an act of cosmic luck that happens once in human history. The ATLAS telescope network operates like a robotic sentinel, scanning enormous chunks of sky multiple times each night. 4 telescope stations spread across Hawaii and South Africa photograph the same stellar fields repeatedly, comparing images to detect anything that moves against the background of distant stars. The system processes over 100 gigabytes of data every single night, analyzing millions of individual stellar positions with machine learning algorithms. Finding 3I-ATLAS required detecting a dot of light that moved just enough between photographs to register as motion, but not so much that it appeared as a streak or blur. The object's hyperbolic velocity means it crosses the sky faster than typical asteroids or comets, creating a detection window measured in days rather than months. Miss that window, and the visitor disappears forever into the darkness beyond our solar system. The artificial intelligence systems had to distinguish 3I-ATLAS from thousands of false positives generated every night. Cosmic rays, striking telescope sensors, create bright spots that mimic moving objects. Satellites and space debris produce streaks that confuse detection algorithms. Even birds, flying in front of telescope lenses, can trigger alerts that waste precious observing time. Machine learning algorithms, trained on years of sky survey data, learn to recognize the subtle patterns that indicate genuine astronomical objects versus instrumental artifacts. 3I-ATLAS appeared as a point source that moved at consistent velocity across multiple images, following a trajectory that matched gravitational physics rather than random noise or equipment malfunction. The timing of discovery represents astronomical serendipity. 3I-ATLAS happened to pass through regions of sky that ATLAS surveys regularly during clear weather conditions that allowed telescopes to operate normally. Cloud cover, equipment maintenance, or even routine calibration procedures could have prevented detection entirely. The object would have sailed through our solar system unnoticed, a cosmic visitor that humanity never knew existed. Once flagged by machine learning systems, 3I-ATLAS triggered an international alert network that connects observatories around the globe. The Minor Planet Center in Cambridge coordinates these discoveries, verifying initial observations and calculating preliminary orbits. Within hours of the ATLAS detection, telescopes in multiple countries were tracking this interstellar intruder. The follow-up observations revealed the true scale of what had been discovered. Ground-based telescopes measured the object's brightness and estimated its size. Spectroscopic instruments began analyzing the light reflected from 3I-ATLAS, revealing the chemical composition of its surface materials. Radio telescopes searched for any signals that might indicate artificial origin, while infrared instruments measured heat emission to determine internal structure. The global response demonstrates how modern astronomy operates as a coordinated international effort. Space agencies, universities, and research institutions shared telescope time and data processing resources to maximize scientific return from this rare opportunity. Observing schedules were reorganized to prioritize 3I-ATLAS measurements, recognizing that interstellar visitors provide unique windows into stellar systems beyond our own. Computer models began predicting the object's future trajectory, calculating optimal viewing opportunities before it disappeared forever. The mathematics revealed that 3I-ATLAS would remain visible to Earth-based telescopes for only a few months before fading beyond detection limits. However, the chemical analysis would soon reveal signatures that had never been observed in nature. 3I-ATLAS bleeds chemicals that should not exist together in any natural object known to science. When the first spectroscopic measurements arrived from major observatories, astronomers found themselves staring at data that violated basic expectations about comet chemistry. Every previous comet studied by humanity shows specific ratios of water, carbon monoxide, and carbon dioxide that reflect formation conditions in the outer regions of stellar systems. 3I-ATLAS shattered these patterns completely. The initial chemical fingerprint revealed carbon dioxide emissions, dominating everything else. Typical comets release mostly water vapor when heated by approaching stars, creating the familiar bright tails visible to amateur astronomers. 3I-ATLAS instead spews carbon dioxide at ratios that dwarf water production by factors that should be physically impossible under normal formation scenarios. Spectroscopic analysis works by spreading the light from 3I-ATLAS into its component colors, revealing absorption and emission lines that correspond to specific molecules. Each chemical compound absorbs and emits light at characteristic wavelengths, creating a unique fingerprint that allows astronomers to identify materials across interstellar distances. The spectrum of 3I-ATLAS showed lines corresponding to carbon dioxide so intense they overwhelmed nearly everything else. The chemistry gets stranger when examining what should be present but appears absent or depleted. Water vapor, the most common volatile material in comets throughout our solar system, appears in 3I-ATLAS at concentrations far below normal levels. Carbon monoxide, typically abundant in objects formed in cold outer regions of stellar systems, shows up in smaller quantities than expected for an interstellar visitor. Even more puzzling are the organic chemistry signatures. 3I-ATLAS shows evidence of complex carbon chain molecules, but in ratios different from any comet previously studied. The object appears to contain cyanide compounds, revealed through characteristic emission lines in the ultraviolet spectrum. These molecules suggest formation conditions or processing mechanisms that remain poorly understood. The chemical anomalies extend beyond simple molecular ratios to isotopic compositions that reveal formation history. Different isotopes of the same element form under specific temperature and pressure conditions, creating signatures that persist for billions of years. 3I-ATLAS shows isotopic ratios that suggest formation in environments with different stellar radiation fields and chemical abundances than exist in our solar neighborhood. Professional chemists and planetary scientists began proposing exotic formation scenarios to explain these observations. Perhaps 3I-ATLAS formed in a stellar system with unusual metallicity, where the abundance of heavy elements differed significantly from solar values. Alternative theories suggested processing by interstellar radiation over billions of years might have altered surface chemistry through mechanisms unknown in our solar system. The strangest possibility involved formation beyond the traditional ice lines where different volatile materials freeze out of protoplanetary disks. 3I-ATLAS might represent materials that condensed in regions where carbon dioxide dominates over water ice, requiring stellar system architectures completely different from our own solar system's organization. Laboratory experiments cannot replicate the conditions 3I-ATLAS experienced during formation and subsequent billion-year journey through interstellar space. The object carries chemical signatures of environments and processes that exist nowhere in our local cosmic neighborhood, making it a unique laboratory for studying exotic astrophysical chemistry. Yet, the carbon dioxide emissions reveal an even more industrial-scale mystery. 3I-ATLAS produces carbon dioxide at rates that rival industrial manufacturing plants on Earth. The James Webb Space Telescope measurements revealed 3I-ATLAS expelling 129 kilograms of carbon dioxide every single second. To put this in perspective, imagine a factory assembly line producing carbon dioxide continuously at the rate of a small automobile every few seconds. This production level creates an invisible cloud of gas extending over 200,000 miles from the comet's nucleus. The carbon dioxide to water ratio, measured at 8:1, represents the most extreme imbalance ever recorded in any comet. Typical solar system comets show ratios closer to 1:10 in the opposite direction, with water dominating carbon dioxide by enormous margins. 3I-ATLAS inverts this relationship so completely that it challenges fundamental models of how volatile materials freeze and organize in protoplanetary disks. Understanding these emission rates requires examining the physics of comet activation. As 3I-ATLAS approaches our Sun, solar radiation heats its surface, causing frozen materials to sublimate directly from solid to gas without melting. The process resembles dry ice evaporating in warm air, but scaled up to geological proportions and sustained for months as the comet follows its hyperbolic trajectory. The energy balance calculations reveal puzzling aspects of this process. Carbon dioxide sublimates at higher temperatures than water ice, meaning it should activate later as comets approach their parent stars. 3I-ATLAS defies this expectation by showing robust carbon dioxide production, while water emissions remain relatively modest, suggesting unusual surface composition or internal structure. One explanation involves a phenomenon called preferential sublimation, where surface layers enriched in carbon dioxide, ice, create a barrier that prevents water vapor from escaping efficiently. Picture 3I-ATLAS as having developed a carbon dioxide-rich shell over billions of years of interstellar travel, with water ice trapped deeper inside the nucleus, where solar heating cannot reach it effectively. Alternative theories propose that 3I-ATLAS formed in a stellar system where carbon dioxide ice was more abundant than water ice due to different chemical conditions during planet formation. Such systems might exist around stars with different metallicities or radiation environments than our Sun, creating protoplanetary disks with inverted chemical gradients compared to our solar system's organization. The production rates also reveal information about the internal structure and porosity of 3I-ATLAS. High gas production requires efficient pathways for sublimated materials to escape from interior regions where heating penetrates. Computer models suggest the nucleus contains a network of cracks, pores, and cavities that allow gas to percolate through the structure and reach the surface. Spacecraft missions to solar system comets have revealed complex internal architectures with distinct layers of different compositions. 3I-ATLAS might represent an extreme example of such layering, with carbon dioxide-dominated regions separated from water-rich materials by barriers that prevent efficient mixing during the sublimation process. The massive carbon dioxide cloud surrounding 3I-ATLAS creates observational opportunities and challenges for astronomers. Infrared telescopes can map the three-dimensional structure of this gas cloud, revealing information about wind patterns and heating mechanisms that remain invisible in visible light observations. However, the cloud also obscures the nucleus itself, making direct measurements of the central object difficult. But hidden within this carbon dioxide factory lies an even stranger chemical mystery. 3I-ATLAS emits metallic nickel vapor without any trace of iron, a chemical signature that has never been observed in nature. The Very Large Telescope in Chile detected atomic nickel emission lines in the spectrum of 3I-ATLAS, using instruments sensitive enough to identify individual elements in the comet's coma. Nickel appears as characteristic green emission lines at specific wavelengths, created when nickel atoms get excited by solar radiation and re-emit light at frequencies determined by quantum mechanical energy levels. The detection itself represents remarkable astronomical detective work. Nickel emissions from comets are extremely faint, requiring long exposure times with the world's most sensitive spectrographs. The signal from 3I-ATLAS showed up clearly in multiple independent observations, confirming that this interstellar visitor releases significant quantities of metallic nickel vapor as it approaches our Sunday. What makes this discovery extraordinary is the complete absence of iron emissions in the same spectrum. Throughout the known universe, nickel and iron appear together in consistent ratios, determined by nuclear physics processes inside stars. These elements form through similar stellar nucleosynthesis reactions and get incorporated into planets and smaller bodies in predictable proportions. Finding nickel without iron violates fundamental expectations about cosmic chemistry. On Earth, nickel and iron occur together in meteorites, planetary cores, and industrial alloys because they share similar chemical properties and formation mechanisms. The ratio of nickel to iron in solar system objects reflects the original composition of the stellar nebula from which our planets formed. 3I-ATLAS breaks this pattern so completely that it suggests formation processes or subsequent processing that remain unknown to science. The nickel emissions from 3I-ATLAS also show unusual time-variable behavior that defies conventional understanding. Between July and August 2025, the intensity of nickel emission lines increased by a factor of 25, following a steep mathematical progression that suggests systematic changes in the comet's internal structure or surface composition. Laboratory studies of nickel-iron separation require extreme conditions involving high-temperature industrial processes or exotic chemistry not found in natural environments. Smelting operations, electrochemical processing, and specialized metallurgy can separate these elements, but such processes require technological capabilities and energy sources unavailable in space environments. Some researchers propose that 3I-ATLAS might contain nickel-rich minerals that sublimate at different rates than iron-bearing compounds. Under this scenario, surface heating preferentially releases nickel-containing materials, while iron remains locked in more thermally stable compounds deeper within the nucleus. However, No known mineral phases show such extreme fractionation between these chemically similar elements. Alternative explanations involve exotic formation conditions in the stellar system where 3I-ATLAS originated. Perhaps unusual stellar radiation environments or magnetic field configurations during planet formation created chemical separation mechanisms unknown in our solar system. The object might represent materials processed by phenomena that exist only in specific types of stellar systems with different physical conditions. The possibility of artificial processing cannot be dismissed entirely, though it remains highly speculative. Industrial separation of nickel from iron produces waste streams enriched in pure nickel, creating signatures that might persist if incorporated into larger objects. However, such processing would require technological civilizations and manufacturing capabilities operating on scales far beyond current human industrial capacity. The metallic emissions pattern sparked discussions about artificial origins that would soon reach public attention. 3I-ATLAS endured longer in the harsh depths of interstellar space than most galaxies have existed. Computer models tracing the trajectory of 3I-ATLAS backward through time suggest this object has been wandering between stars for potentially 7 to 14 billion years. To appreciate this timescale, consider that our entire solar system formed only 4.6 billion years ago. 3I-ATLAS might have been ejected from its parent system when the universe was less than half its current age. Surviving such timeframes in interstellar space requires withstanding environmental conditions that destroy smaller objects within millions of years. Cosmic rays, high-energy particles, accelerated by supernova explosions and other violent astrophysical events, constantly bombard objects traveling between stars. These particles penetrate surface layers and create chemical changes that alter composition and structure over geological time periods. The radiation environment between stars differs dramatically from conditions within stellar systems where planets and comets form. Interstellar space contains dilute gas and dust, but lacks the protective magnetic fields and stellar winds that shield objects in orbit around stars. 3I-ATLAS experienced direct exposure to galactic cosmic radiation for billions of years, yet somehow preserved its internal structure and chemical composition. Research into cosmic ray processing of small bodies suggests that objects smaller than several kilometers across get disrupted or chemically altered beyond recognition during extended interstellar journeys. 3I-ATLAS exceeds this critical size threshold by substantial margins, allowing it to survive the bombardment that would destroy smaller interstellar wanderers. The surface of 3I-ATLAS likely developed what researchers call a radiation-processed crust during its billion-year journey. Cosmic ray impacts break chemical bonds in surface materials, creating new compounds and altering the physical properties of the outer layers. This processing might explain some of the unusual chemical signatures observed in spectroscopic measurements. Laboratory experiments using particle accelerators to simulate cosmic ray bombardment show that organic molecules get destroyed or transformed into simpler compounds over timescales much shorter than the age of 3I-ATLAS. Yet this object shows evidence of complex carbon chemistry, suggesting either formation with unusual organic compositions or protection mechanisms that preserve these materials during interstellar travel. The internal temperature of 3I-ATLAS during its journey remained close to absolute zero, around -400 degrees Fahrenheit. At these temperatures, chemical reactions proceed extremely slowly, helping preserve the original composition formed billions of years ago in its parent stellar system. The object essentially became a frozen time capsule, carrying pristine samples of ancient planetary formation materials. Gravitational interactions with passing stars might have altered the orbit of 3I-ATLAS multiple times during its interstellar journey. Computer simulations suggest objects with such long travel times encounter numerous stellar systems, receiving gravitational perturbations that change their trajectories and speeds. 3I-ATLAS survived these encounters without fragmentation or capture by other stellar systems. The thickness of any radiation-processed surface layer provides clues about the duration of interstellar travel. Spectroscopic measurements probe only the outermost surface materials, meaning the unusual chemistry observed might represent billions of years of cosmic ray processing rather than original formation conditions. Deeper layers might preserve materials with compositions more similar to typical solar system objects. However, the origin point of this ancient wanderer reveals even more mysteries about galactic evolution. 3I-ATLAS originated from the most ancient and violent region of our galaxy, carrying chemical signatures from cosmic dawn. Astronomers traced the trajectory of 3I-ATLAS backward through space and time, using computer simulations that account for the gravitational influence of billions of stars over millions of years. These calculations point toward the galactic thick disk, a population of ancient stars formed when the Milky Way was young and chaotic, approximately 10 billion years ago. The thick disk represents a fossil record of our galaxy's violent youth, when star formation proceeded at rates 10 times higher than today, and massive stellar explosions enriched interstellar space with heavy elements. Stars in this population show chemical compositions dramatically different from our Sun, with lower abundances of elements heavier than hydrogen and helium. 3I-ATLAS carries these ancient chemical fingerprints. Understanding galactic structure requires visualizing the Milky Way as consisting of distinct components formed at different epochs. The thin disk, where our solar system resides, contains younger stars formed from gas already enriched with heavy elements from previous generations of stellar evolution. The thick disk preserves stars formed earlier, when chemical enrichment remained incomplete and stellar formation followed different patterns. Chemical analysis of 3I-ATLAS reveals metallicity consistent with thick disk stellar populations. The term metallicity refers to the abundance of elements heavier than hydrogen and helium, which astronomers call metals, regardless of their actual chemical properties. Objects formed around thick disk stars show metal abundances approximately 40% of solar values, matching observations of 3I-ATLAS. The velocity of 3I-ATLAS also supports thick disk origin. Objects ejected from stellar systems inherit some of the orbital motion of their parent stars around the galactic center. Thick disk stars move in highly elliptical orbits that carry them far above and below the galactic plane, creating velocity distributions different from thin disk populations. 3I-ATLAS shows kinematic properties consistent with ejection from thick disk stellar systems. Formation in the thick disk environment would subject 3I-ATLAS to conditions absent in our local galactic neighborhood. Higher stellar densities increase the frequency of gravitational encounters that can eject comets and asteroids from planetary systems. More massive stars produce stronger stellar winds and radiation fields that alter the chemistry of nearby protoplanetary disks during planet formation. The chemical composition of 3I-ATLAS might reflect these exotic formation conditions. Lower metallicity environments produce protoplanetary disks with different ice lines and volatile distributions compared to systems forming today. Carbon dioxide might become more abundant relative to water in stellar systems with different radiation environments or chemical abundances than exist around solar-type stars. Research into thick disk stellar populations shows they formed during an epoch when the galaxy underwent major merger events with smaller satellite galaxies. These collisions triggered bursts of star formation and created the chaotic gravitational environment that scattered objects like 3I-ATLAS into interstellar space. The object might represent debris from planetary formation processes, operating under conditions dramatically different from those in our solar system. Dating thick disk stellar populations suggests 3I-ATLAS formed during the era astronomers call cosmic noon, approximately 2 to 3 billion years after the Big Bang. This period marked peak star formation rates across the universe, when the first heavy elements were being incorporated into planetary systems and the chemical evolution of galaxies proceeded most rapidly. The implications extend far beyond a single wandering comet to questions about the abundance of such massive interstellar objects. 3I-ATLAS weighs 10 million times more than previous interstellar visitors, creating statistical impossibilities that challenge our understanding of what roams between stars. The 7-mile diameter of 3I-ATLAS translates to approximately 1 trillion kilograms of mass, assuming density similar to typical comet nuclei composed of ice and rock. This estimate makes 3I-ATLAS comparable in mass to some of the largest asteroids in our solar system, while moving at speeds that dwarf anything gravitationally bound to our Sunday. Comparing 3I-ATLAS to previous interstellar visitors reveals the scale of this discovery. Oumuamua, the first confirmed interstellar object, measured roughly 400 meters in length with an estimated mass around 10 million kilograms. Borisov, the first interstellar comet, showed a nucleus diameter of approximately 1 kilometer with mass estimates around 1 billion kilograms. 3I-ATLAS dwarfs both predecessors by factors that strain statistical credibility. The mathematics of object size distributions in space follow power laws that predict the relative abundance of different sized bodies. Small objects vastly outnumber large ones, with the relationship typically showing 10 times more objects at each factor of 10 decrease in size. Finding 3I-ATLAS after only 3 interstellar detections violates these statistical expectations by enormous margins. Professional astronomers calculated that discovering an object the size of 3I-ATLAS should require detecting millions of smaller interstellar visitors first. The probability of finding such a massive object among the first few interstellar detections approaches statistical impossibility under conventional models of what gets ejected from planetary systems throughout the galaxy. This mass discrepancy suggests fundamental gaps in our understanding of either interstellar object populations or the ejection mechanisms that create them. Perhaps giant planets are more efficient at ejecting large objects than smaller ones, creating size distributions different from expectations based on solar system asteroid and comet populations. Alternative explanations involve selection effects that make large objects easier to detect, despite their lower abundance. The gravitational binding energy required to eject 3I-ATLAS from its parent stellar system exceeds the energy available from most planetary interactions. Computer simulations show that removing objects this massive requires encounters with planets at least as large as Jupiter, occurring under precisely defined geometric configurations that maximize energy transfer efficiency. More exotic ejection scenarios involve stellar binary systems, where 2 stars orbit each other with periods that create resonant interactions with planetary orbits. During specific orbital alignments, gravitational forces can amplify to levels sufficient for ejecting even massive objects like 3I-ATLAS. However, such mechanisms require fine-tuned initial conditions that may be rare in typical stellar systems. The survival of 3I-ATLAS during billions of years of interstellar travel also depends on its large size. Smaller objects experience proportionally higher surface-to-volume ratios that make them vulnerable to erosion by cosmic rays and interstellar dust impact. 3I-ATLAS maintained sufficient mass to preserve its internal structure and chemical composition, despite extended exposure to the harsh interstellar environment. Current surveys for interstellar objects remain biased toward detecting larger, brighter objects that reflect sufficient sunlight for ground-based telescopes to identify. 3I-ATLAS might represent the visible tip of a vast population of interstellar wanderers that remain below detection thresholds due to size or composition constraints. Yet even more puzzling than its mass is the mathematical impossibility of its orbital alignment. 3I-ATLAS follows a trajectory so perfectly aligned with our solar system that random chance becomes mathematically absurd. The orbital inclination of 3I-ATLAS measures just 5 degrees from the ecliptic plane, the imaginary disk where Earth and other planets orbit our Sunday. For comparison, most objects approaching from interstellar space should arrive from random directions, creating orbital inclinations distributed equally across all possible angles. Finding an interstellar visitor aligned so closely with our planetary system occurs with probability less than 0.2%. Understanding orbital mechanics requires visualizing three-dimensional space where objects can approach from any direction on an imaginary sphere surrounding our solar system. Random arrivals should distribute uniformly across this sphere, with most trajectories inclined at high angles relative to our planetary orbits. 3I-ATLAS, instead, approaches nearly within the same plane occupied by Earth, Mars, Jupiter, and Saturn. The mathematical analysis extends beyond simple inclination to include other orbital parameters that compound the statistical improbability. 3I-ATLAS approaches our Sun in retrograde motion, traveling opposite to the direction planets orbit. Retrograde interstellar objects are expected, but when combined with low inclination, the probability drops to levels that challenge random occurrence. Professional statisticians and astronomers calculated the combined probability of all observed orbital characteristics occurring by chance. The analysis includes approach, velocity, inclination angle, retrograde motion, and timing of discovery relative to perihelion passage. Multiple independent calculations confirm that such alignment should occur less frequently than once per several thousand interstellar object encounters. The timing aspect adds another layer of improbability. 3I-ATLAS was discovered at optimal distance and brightness for detailed study, allowing months of observations before fading beyond detection limits. Random discovery timing should distribute uniformly throughout the object's passage through our solar system. Yet 3I-ATLAS appeared precisely when ground-based telescopes could characterize it most effectively. Some researchers propose anthropic selection effects to explain these statistical anomalies. Perhaps interstellar objects with orbital characteristics similar to 3I-ATLAS are more easily detected and studied, creating observational bias that makes such discoveries appear more common than they actually are. However, the magnitude of probability involved exceeds typical selection effects by several orders of magnitude. Alternative explanations invoke gravitational focusing mechanisms that might preferentially direct interstellar objects towards specific orbital orientations. The gravitational field of our galaxy creates subtle effects that could influence the trajectories of objects traveling between stars over billion-year timescales. However, detailed calculations show such effects remain too weak to explain the observed orbital alignment. More speculative theories suggest that 3I-ATLAS might not represent a random interstellar wanderer, but instead originate from a stellar system with specific geometric relationship to our solar system. Objects ejected from stellar systems in our local galactic neighborhood might show preferential orbital orientations due to shared motion around the galactic center. The discovery sequence itself adds statistical complexity. Finding 3 interstellar objects in less than a decade, after centuries of astronomical observation, suggests either remarkable coincidence or systematic changes in detection capabilities. The rapid succession of discoveries might indicate that interstellar visitors are far more common than previously assumed. However, advanced space telescope observations would soon reveal chemical signatures that defy all conventional explanations. The most powerful space telescope ever built revealed chemistry in 3I-ATLAS that challenges the laws of physics. When the James Webb Space Telescope turned its instruments toward 3I-ATLAS in August 2025, astronomers expected to confirm basic comet chemistry with improved precision and sensitivity. Instead, Webb detected molecular signatures that violate fundamental expectations about how matter behaves in space environments. The Webb telescope operates in infrared wavelengths that penetrate dust and gas to reveal molecular compositions invisible to ground-based instruments. Its 18-segment primary mirror, larger than a tennis court when fully deployed, collects enough light to analyze the chemical fingerprints of objects billions of miles away with unprecedented detail and accuracy. Webb's near-infrared spectrograph created spatially resolved maps of different molecules across the coma of 3I-ATLAS, revealing how various chemicals distribute around the nucleus. The instrument detected carbon dioxide concentrations 8 times higher than water vapor, confirming ground-based measurements while providing three-dimensional information about gas cloud, structure, and dynamics. The spatial resolution capabilities of Webb revealed that carbon dioxide emissions concentrate in specific regions around the nucleus, rather than distributing uniformly. This pattern suggests either highly localized surface composition variations or internal structure that channels gas flow through preferred pathways. Neither phenomenon matches expectations for typical comet behavior under solar heating. Webb also detected complex organic molecules in 3I-ATLAS with abundances and ratios different from any solar system comet previously studied. The instrument identified carbon chain compounds, nitrile molecules, and organic polymers that suggest formation or processing under conditions absent in our local cosmic environment. The isotopic composition measurements provided the most startling revelations. Webb's sensitivity allows detection of rare isotopic variants that reveal information about formation conditions and stellar nucleosynthesis processes. 3I-ATLAS shows isotopic ratios for carbon, nitrogen, and oxygen that differ significantly from solar system values and typical interstellar medium compositions. These isotopic signatures suggest 3I-ATLAS formed in a stellar environment with different nuclear physics conditions than exist around our Sunday. Perhaps the object originated around a star with different mass, metallicity, or evolutionary history that produced unique isotopic abundances in its protoplanetary disk during planet formation. Webb's observations also revealed temporal variations in chemical emissions that follow unexpected patterns. Most comets show smooth changes in gas production as they approach and recede from their parent stars. 3I-ATLAS, instead, displays erratic variations in different molecular species that suggest complex internal processes or structural changes occurring during solar heating. The temperature mapping capabilities of Webb showed that 3I-ATLAS maintains surface temperatures consistent with efficient carbon dioxide sublimation while keeping water ice below sublimation thresholds. This thermal behavior requires unusual surface composition or structure that preferentially releases carbon dioxide while preserving water in solid form. Perhaps most puzzling are the negative detections, molecules that should be present but remain absent from Webb's sensitive observations. 3I-ATLAS shows no evidence of methane, ammonia, or hydrogen sulfide, common volatile compounds found in most solar system comets. The absence of these materials suggests formation under chemical conditions dramatically different from typical comet-forming regions. But the strangest discovery would emerge from measurements of metallic elements that sparked controversial theories about artificial origins. 3I-ATLAS emits metallic nickel vapor in patterns that have never occurred in nature, triggering debates about artificial manufacturing processes. The detection of atomic nickel emission from 3I-ATLAS required the most sensitive ground-based spectrographs operating at their detection limits. The Very Large Telescope in Chile used adaptive optics systems to compensate for atmospheric turbulence, achieving resolution sharp enough to separate nickel emission lines from contaminating signals in the crowded optical spectrum. Nickel atoms in the coma of 3I-ATLAS emit characteristic green light at wavelengths of 527.03 nanometers when excited by solar radiation. This emission line appears distinct from other metallic elements and provides unambiguous identification of nickel vapor in space environments. The signal from 3I-ATLAS exceeded background noise levels by factors sufficient to confirm genuine detection. The intensity of nickel emissions from 3I-ATLAS increased by 25 times between July and August 2025, following a steep mathematical progression that suggests systematic changes in surface composition or internal structure. This behavior differs dramatically from typical cometary outgassing patterns, which usually show smooth variations correlated with solar distance and heating rates. Laboratory studies of nickel-bearing meteorites and asteroid samples show that nickel typically occurs combined with iron in metallic alloys or bound in silicate minerals. Releasing atomic nickel vapor requires heating these materials to temperatures exceeding 1000 degrees Celsius, far higher than surface temperatures achieved by solar heating at the distance of 3I-ATLAS from our Sunday. The complete absence of iron emissions in the same spectrum creates a chemical signature unknown in natural space environments. Throughout the observable universe, nickel and iron appear together in ratios determined by stellar nucleosynthesis processes that create these elements through similar nuclear reactions. Separating nickel from iron requires industrial processes or extreme physical conditions absent in typical astronomical environments. On Earth, nickel separation from iron involves high-temperature smelting operations, electrochemical processing, or specialized metallurgical techniques developed for industrial applications. These processes require technological infrastructure and energy sources unavailable in space environments, raising questions about how 3I-ATLAS could produce similar chemical signatures through natural mechanisms. Some researchers proposed exotic mineralogy explanations involving rare nickel-rich compounds that might sublimate at different rates than iron-bearing minerals. However, no known mineral phases show the extreme fractionation between nickel and iron observed in 3I-ATLAS emissions. The chemical behavior violates fundamental principles of thermodynamics and materials science. Alternative theories invoke unusual formation conditions in the stellar system where 3I-ATLAS originated. Perhaps magnetic field configurations during planet formation created chemical separation mechanisms unknown in our solar system. Or stellar radiation environments might have processed surface materials through photochemical reactions that preferentially released nickel while preserving iron in non-volatile compounds. The time-variable behavior of nickel emissions adds complexity that challenges all proposed natural explanations. The 25-fold intensity increase follows mathematical patterns reminiscent of systematic processing rather than random geological or chemical phenomena. Such organized behavior typically indicates controlled rather than chaotic underlying mechanisms. Harvard physicist Avi Loeb noted that the nickel without iron signature, combined with orbital characteristics and timing of discovery, creates multiple statistical anomalies that individually might occur naturally, but collectively suggest systematic, rather than random origins. His analysis sparked public discussions about whether 3I-ATLAS might represent artificial technology rather than natural astronomical phenomena. These speculative theories would soon require official responses from space agencies concerned about public misconceptions. Space agencies found themselves forced to publicly address growing speculation that 3I-ATLAS might be artificial technology from another civilization. The combination of unusual orbital characteristics, unprecedented chemical signatures, and statistical improbabilities surrounding 3I-ATLAS generated online theories suggesting the object might represent artificial rather than natural origins. Social media platforms and astronomy forums buzzed with discussions comparing 3I-ATLAS to science fiction depictions of alien spacecraft or automated probes. Harvard physicist Avi Loeb, known for previous controversial suggestions about Oumuamua, published detailed analyses suggesting 3I-ATLAS showed multiple characteristics inconsistent with natural astronomical objects. His Loeb scale rated the object as 4 out of 10 for artificial likelihood, based on orbital alignment, chemical anomalies, and discovery timing that individually might occur naturally but collectively suggested systematic rather than random phenomena. The rapid spread of these theories through internet communities prompted official responses from NASA, the European Space Agency, and major astronomical organizations. These institutions recognized the need to address public misconceptions before speculation overwhelmed scientific analysis with unfounded claims about extraterrestrial visitation. NASA issued comprehensive statements explaining the natural phenomena that could account for the unusual characteristics of 3I-ATLAS. The agency emphasized that comet nuclei can develop complex internal structures and chemical compositions through billions of years of evolution in interstellar space, creating signatures different from typical solar system objects without requiring artificial origins. The nickel without iron emissions received particular attention in official statements. NASA scientists explained that selective sublimation processes could preferentially release certain metallic elements while keeping others bound in thermally stable compounds. The agency cited laboratory studies of meteorite compositions showing that rare mineral phases might account for unusual elemental ratios under specific heating conditions. Space agency responses also addressed the statistical improbabilities surrounding orbital characteristics and discovery timing. Officials noted that detection bias affects interstellar object surveys, making objects with specific orbital orientations more likely to be discovered and studied than those approaching from random directions. The apparent statistical anomalies might reflect observational selection effects rather than genuine improbabilities. Professional astronomers emphasized the importance of applying scientific methodology to analyze unusual phenomena rather than jumping to extraordinary conclusions without exhausting natural explanations. The scientific process requires testing conventional hypotheses before considering more speculative alternatives, even when dealing with genuinely anomalous observations. Multiple independent research groups confirmed that 3I-ATLAS exhibits normal cometary behavior, including dust emission, gas production, and coma development consistent with solar heating of volatile materials. Infrared observations showed thermal signatures matching expectations for rocky icy composition, while photometric measurements revealed surface properties similar to other comet nuclei. Radio telescope searches for artificial signals from 3I-ATLAS detected no emissions beyond natural thermal radiation and reflected sunlight. The Search for Extraterrestrial Intelligence Institute monitored the object across multiple frequency bands without finding evidence of technological activity or communication attempts. The scientific consensus emerging from detailed analysis concluded that 3I-ATLAS represents an unusual but natural interstellar comet, with characteristics shaped by formation conditions and processing mechanisms different from objects in our solar system. The unusual properties reflect the diversity of planetary formation environments throughout the galaxy rather than artificial construction. However, the approaching perihelion passage would create unprecedented opportunities for detailed study during the most dramatic phase of this cosmic visitor's journey. 3I-ATLAS will reach its closest approach to our Sun, precisely when Earth cannot observe the most dramatic moment in this cosmic visitor's billion-year journey. Perihelion passage occurs on October 30th, 2025, when 3I-ATLAS reaches its minimum distance of 1.36 astronomical units from our Sunday. This distance places the comet between Earth and Mars orbits, closer to our star than any previous interstellar visitor has approached during human observation. However, the timing creates an astronomical tragedy of cosmic proportions. During October perihelion, 3I-ATLAS will be positioned directly behind the Sun from Earth's perspective, creating what astronomers call solar conjunction. The brilliant disk of our star completely overwhelms any light reflected from the comet, making direct observation impossible with even the most powerful ground-based telescopes. This celestial alignment means humanity will miss the peak activity phase when 3I-ATLAS reaches maximum gas production and potentially develops its largest tail. The physics of perihelion passage promises spectacular transformations that remain hidden from view. Solar heating intensifies dramatically as 3I-ATLAS approaches, potentially increasing carbon dioxide production rates from current levels of 129 kilograms per second to several times higher values. Surface temperatures could reach levels sufficient to sublimate water ice buried beneath the carbon dioxide-rich outer layers. Computer models predict that perihelion heating might trigger structural changes in the nucleus of 3I-ATLAS as internal pressure from sublimating gases creates stress fractures or explosive outgassing events. Comet nuclei occasionally fragment during close solar approaches when internal heating overcomes gravitational binding forces, creating multiple smaller objects with enhanced surface area for gas production. The tail development during perihelion represents the most visually dramatic aspect hidden from Earth-based observation. As 3I-ATLAS approaches the Sun, solar radiation pressure and stellar wind interactions will accelerate gas and dust particles away from the nucleus, potentially creating tail structures extending millions of kilometers into space. The retrograde orbital motion might produce unusual tail orientations different from typical solar system comets. Ground-based observatories planned coordinated observation campaigns for September and November, bracketing the hidden perihelion passage with detailed measurements of pre- and post-perihelion activity levels. These observations will document changes in gas production, dust emission rates, and chemical composition that reveal information about internal structure and heating mechanisms. The solar conjunction problem affects all Earth-based telescopes regardless of size or location. Space-based observatories like Hubble and James Webb face similar limitations when observing objects positioned too close to the Sun's apparent location in the sky. Solar panels and sensitive instruments must be protected from direct solar radiation, preventing observations of targets within specific angular distances from our star. Radio telescopes can potentially observe 3I-ATLAS during solar conjunction by detecting thermal emissions at wavelengths where the Sun appears less bright relative to other sources. However, radio observations provide limited information about chemical composition and structural details compared to optical and infrared measurements that require direct imaging capabilities. The timing of solar conjunction represents astronomical misfortune, compounded by the rarity of interstellar visitor encounters. Humanity might wait decades or centuries before another object of comparable size and scientific interest approaches our solar system, making the observational gap during perihelion passage particularly frustrating for researchers studying interstellar comet behavior. Fortunately, spacecraft positioned throughout our solar system will provide unique viewing opportunities unavailable from Earth. Spacecraft orbiting Mars will capture humanity's only close-up views of 3I-ATLAS during its most active and dangerous phase. The Mars Reconnaissance Orbiter, Europe's Mars Express, and the ExoMars Trace Gas Orbiter occupy perfect positions to observe 3I-ATLAS during its October close approach to the Red Planet. These robotic sentinels will achieve viewing angles impossible from Earth, potentially providing 3 times better resolution than Hubble Space Telescope observations during the comet's peak activity period. Mars reaches opposition to 3I-ATLAS on October 3rd, positioning the planet optimally for detailed observations when the interstellar visitor passes within 47 million kilometers of the Red Planet. This distance represents closer proximity than 3I-ATLAS achieves to Earth, creating unprecedented opportunities for high-resolution imaging and spectroscopic analysis. The Mars Reconnaissance Orbiter carries the high-resolution Imaging Science Experiment camera, capable of resolving surface features smaller than 1 meter across on Mars from orbital altitude. When pointed toward 3I-ATLAS, This instrument could potentially detect structural details in the comet's nucleus and map the three-dimensional architecture of gas and dust emissions with resolution impossible from Earth-based telescopes. Europe's Mars Express orbiter contributes complementary capabilities through its visual and infrared mineralogical mapping spectrometer designed to analyze surface compositions on Mars. This instrument can identify specific minerals and chemical compounds in 3I-ATLAS across wavelength ranges optimized for detecting water, carbon dioxide, and organic molecules that reveal information about formation conditions. The ExoMars Trace Gas Orbiter specializes in atmospheric chemistry measurements using ultra-sensitive spectrographs, originally designed to search for trace gases in the Martian atmosphere. These instruments can detect molecular concentrations at parts per billion levels, potentially revealing minor chemical species in 3I-ATLAS that remain below detection thresholds for Earth-based observations. Coordinated observations from multiple Mars orbiters will create stereoscopic imaging opportunities that reveal three-dimensional structure and motion within the coma of 3I-ATLAS. By comparing simultaneous images from different viewing angles, researchers can map gas flow patterns, dust particle trajectories, and internal structure details impossible to determine from single perspective observations. The Perseverance and Curiosity rovers on Mars' surface might detect atmospheric changes caused by dust and gas from 3I-ATLAS entering Mars's thin atmosphere. Sensitive instruments designed to monitor Martian atmospheric chemistry could potentially identify trace contamination from the interstellar visitor, providing ground truth measurements of chemical composition and particle size distributions. Mars orbiters face unique challenges when observing 3I-ATLAS due to their own orbital motion around the red planet. Spacecraft must maintain precise pointing accuracy while moving at orbital velocities exceeding 3 kilometers per second, requiring sophisticated guidance systems to track the fast-moving interstellar target across the stellar background. The timing of Mars observations coincides with dust storm season on the red planet, when atmospheric opacity can interfere with surface-based measurements. However, orbital altitude places Mars spacecraft above most atmospheric effects, providing clear viewing conditions for 3I-ATLAS observations, regardless of surface weather conditions. Data transmission from Mars to Earth requires careful scheduling to avoid interference from solar conjunction effects that also impact communications with interplanetary spacecraft. Mars orbiters must store observational data on board until communication windows provide reliable downlink opportunities to transmit high-resolution images and spectra to ground-based receiving stations. These Mars observations will document activity levels during the cosmic noon phase of 3I-ATLAS evolution. 3I-ATLAS carries pristine materials from cosmic noon, the epoch when star formation peaked across the universe and the first heavy elements emerged. Cosmic noon occurred approximately 2 to 3 billion years after the Big Bang, marking the era when galaxies formed, stars at rates 10 times higher than today, and the universe underwent its most dramatic period of chemical evolution. During this epoch, the first generations of massive stars completed their life cycles, exploding as supernovae that scattered heavy elements throughout space for incorporation into subsequent stellar and planetary systems. The age estimates for 3I-ATLAS place its formation during or shortly after cosmic noon, making this interstellar visitor a direct sample of materials processed during the universe's most dynamic evolutionary phase. The chemical signatures observed in spectroscopic analysis reflect conditions that existed when galaxies were younger, more active, and chemically different from the present-day cosmos. Understanding cosmic noon requires appreciating the scale of universal evolution over 13.8 billion years since the Big Bang. The earliest stars formed from primordial hydrogen and helium, lacking the heavy elements necessary for rocky planet formation. Only after several generations of stellar evolution did sufficient carbon, oxygen, silicon, and iron accumulate in interstellar space to enable complex chemistry and planetary system development. The metallicity measurements of 3I-ATLAS show heavy element abundances consistent with cosmic noon stellar populations. These concentrations fall below solar values but exceed those of the earliest stellar generations, indicating formation during the transitional epoch when heavy element enrichment was progressing rapidly through galactic chemical evolution processes. Star formation rates during cosmic noon exceeded current galactic activity by factors of 10 to 100, creating environments where stellar feedback processes operated under dramatically different conditions than exist today. Higher supernova rates, more frequent stellar collisions, and intense radiation fields from massive stellar associations created chemical processing mechanisms absent in present-day galactic environments. The thick disk stellar population from which 3I-ATLAS likely originated formed during cosmic noon through processes that remain poorly understood. Galaxy merger events, gas accretion from intergalactic space, and gravitational instabilities in early galactic disks created bursts of star formation that established the chemical and kinematic properties observed in thick disk stellar populations today. Protoplanetary disks forming during cosmic noon operated under different physical conditions than those around present-day stars. Higher background radiation levels, different dust grain compositions, and altered ice line locations could produce planetary systems with chemical architectures unlike anything in our local galactic neighborhood. 3I-ATLAS might represent materials formed under these exotic conditions. The isotopic ratios measured in 3I-ATLAS reflect nuclear physics processes occurring in stellar interiors during cosmic noon. Different types of stars dominated stellar populations at that epoch, including massive stars with short lifespans that contributed disproportionately to heavy element production through rapid evolutionary sequences ending in supernova explosions. Laboratory studies cannot replicate cosmic noon conditions due to the vast scales of energy, time, and gravitational influence involved in galactic chemical evolution. 3I-ATLAS provides direct access to materials processed during this crucial epoch, offering unique insights into physical processes that shaped the chemical foundation for all subsequent planetary system formation. The survival of 3I-ATLAS over billion-year timescales preserves chemical signatures that would otherwise remain inaccessible to observational study. This interstellar time capsule carries information about cosmic noon, stellar nucleosynthesis, protoplanetary disk chemistry, and early planetary formation processes, frozen in its internal structure and composition. These ancient materials challenge fundamental assumptions about how planetary systems develop throughout cosmic history. 3I-ATLAS demolishes textbook models of how planets form, revealing that our solar system represents a cosmic anomaly rather than typical behavior. Traditional planetary formation theory assumes that protoplanetary disks around young stars follow predictable patterns where water ice dominates volatile inventories beyond specific distances called ice lines. 3I-ATLAS inverts this fundamental assumption with its extreme carbon dioxide to water ratio of 8:1, suggesting formation in environments where carbon dioxide ice exceeded water ice abundance during planet-building processes. The standard model of planetary formation begins with stellar nebulae collapsing under gravity to form central stars surrounded by rotating disks of gas and dust. As temperatures decrease with distance from the central star, different volatile compounds freeze out at characteristic locations. Water ice beyond approximately 3 astronomical units, carbon dioxide ice farther out, and other compounds at even greater distances. 3I-ATLAS appears to violate these ice line predictions completely. Its chemical composition suggests formation in a region where carbon dioxide remained more abundant than water throughout the planet formation process. requiring environmental conditions absent in our solar system, and most theoretical models of typical protoplanetary disk evolution. Computer simulations of protoplanetary disk chemistry show that achieving carbon dioxide dominance over water requires unusual stellar properties, disk compositions, or radiation environments. Perhaps 3I-ATLAS formed around a star with different luminosity, surface temperature, or evolutionary history that altered the thermal structure and chemical gradients within its surrounding protoplanetary disk. Alternative scenarios involve stellar systems with different heavy element abundances that affect dust, grain compositions, and gas phase chemistry. Stars with metallicities significantly lower or higher than solar values might produce protoplanetary disks with altered volatile inventories, creating conditions where carbon dioxide becomes more abundant than water in planet-forming regions. The implications extend far beyond individual object chemistry to fundamental questions about planetary system diversity throughout the galaxy. If 3I-ATLAS represents typical materials from stellar systems formed during cosmic noon, then billions of planetary systems might have developed chemical architectures completely different from our solar system's organization. This chemical diversity suggests that habitable planet formation might follow pathways unknown in our local cosmic environment. Planets forming in carbon dioxide-rich environments could develop atmospheres, surface conditions, and potentially biological processes based on chemical foundations different from Earth-based life that depends on liquid water availability. The survival and ejection of 3I-ATLAS also reveals information about dynamical processes in its parent planetary system. Objects with unusual chemical compositions might experience different gravitational interactions with forming planets, affecting their final orbital distributions and ejection probabilities compared to typical solar system analogues. Recent exoplanet discoveries show that planetary systems throughout the galaxy display architectural diversity far exceeding early theoretical predictions. Hot Jupiters orbiting close to their stars, super-Earths lacking solar system analogues, and unusual orbital configurations suggest that planetary formation operates under a much broader range of conditions than previously imagined. 3I-ATLAS provides direct chemical evidence supporting this diversity by carrying materials formed under conditions absent in our solar system. The object represents a messenger from planetary formation processes operating according to physical principles and environmental parameters different from those that created Earth and its neighboring planets. Understanding the formation history encoded in 3I-ATLAS requires detailed laboratory analysis of materials that will never be available for direct study. The object will continue its journey into interstellar space, taking its chemical secrets beyond reach of spacecraft missions or sample return opportunities. Yet these ancient materials might play active roles in seeding planetary formation around young stars throughout the galaxy. 3I-ATLAS preserves materials older than our entire solar system in chemically pristine condition, creating a traveling laboratory of primordial cosmic materials. The 7 to 14 billion year age estimates for 3I-ATLAS mean this object contains materials that formed when the universe was less than half its current age. These ancient substances survived billions of years of exposure to cosmic radiation, interstellar chemistry, and gravitational perturbations, while maintaining chemical signatures recognizable to modern spectroscopic analysis. Preservation of primordial materials requires protection from processes that normally alter or destroy chemical compounds over geological timescales. Cosmic ray bombardment creates nuclear transmutation reactions that change elemental compositions. Ultraviolet radiation from distant stars breaks chemical bonds in organic molecules. Impacts with interstellar dust particles erode surface layers and mix materials from different formation epochs. The large size of 3I-ATLAS provides crucial protection through favorable surface-to-volume ratios that minimize external processing relative to internal preservation. Small interstellar objects experience proportionally higher surface exposure that destroys primordial signatures within millions of years. 3I-ATLAS maintains sufficient bulk to preserve internal materials from cosmic ray penetration and surface erosion. Temperature conditions during interstellar travel also favor chemical preservation. The nucleus of 3I-ATLAS remained at temperatures approaching absolute zero throughout its billion-year journey, effectively freezing all chemical reactions and preventing thermal processing that would alter original compositions. This deep freeze preserved volatile compounds and organic molecules that would decompose under warmer conditions. Laboratory studies of meteorites and lunar samples show that space weathering processes can alter surface compositions within thousands to millions of years of exposure. 3I-ATLAS endured exposure times orders of magnitude longer while preserving chemical signatures detectable through modern observational techniques, suggesting unusual protective mechanisms or formation with exceptionally stable material compositions. The chemical analysis revealing complex organic molecules, unusual isotopic ratios, and exotic volatile compositions indicates that 3I-ATLAS carries direct samples of primordial materials from its formation epoch. These signatures represent fossilized chemistry from stellar nucleosynthesis processes, protoplanetary disk evolution, and early planetary formation mechanisms operating under conditions different from those in our solar system. Isotopic measurements provide the most robust evidence for primordial preservation. Different isotopes of the same element form through specific nuclear physics processes in stellar interiors, creating signatures that persist through subsequent chemical processing unless altered by nuclear reactions. 3I-ATLAS shows isotopic ratios reflecting stellar nucleosynthesis conditions from its formation epoch. The organic chemistry detected in 3I-ATLAS includes carbon chain molecules and nitrile compounds that typically decompose under cosmic ray bombardment within millions of years. Finding these compounds after billion-year interstellar exposure suggests either formation with unusually stable organic compositions or protection mechanisms that prevented radiation damage throughout the journey. Comparison with solar system materials reveals the extent of chemical preservation in 3I-ATLAS. Meteorites from our asteroid belt, formed 4.6 billion years ago, show extensive alteration from solar heating, planetary interactions, and space weathering processes. 3I-ATLAS preserves signatures from potentially twice this age, while maintaining less alteration than typical solar system objects. The pristine nature of materials in 3I-ATLAS creates unique opportunities for studying cosmic chemical evolution through direct observation rather than theoretical modeling. This interstellar visitor provides access to formation conditions and processing mechanisms that remain otherwise inaccessible to observational astronomy or laboratory investigation. These preserved ancient materials might actively participate in creating the next generation of planetary systems. 3I-ATLAS might function as a galactic seed pod, carrying the building blocks needed to jumpstart planet formation around infant stars. Recent theoretical work by Suzanne Falsner and colleagues suggests that interstellar objects like 3I-ATLAS could solve fundamental problems in planetary formation theory by providing ready-made building blocks for planetary accretion around young stellar systems. Traditional models struggle to explain how microscopic dust particles grow to planetary sizes without getting swept into central stars during the process. The meter barrier problem in planetary formation theory describes the difficulty of growing objects from centimeter to kilometer sizes through collisional processes. Objects in this size range experience strong aerodynamic drag from gas in protoplanetary disks, causing them to spiral inward towards central stars faster than they can grow through accumulation of additional material. 3I-ATLAS bypasses this barrier entirely by providing pre-assembled kilometer-sized building blocks. Computer simulations show that interstellar objects captured by young stellar systems can significantly accelerate giant planet formation by serving as condensation nuclei for gas and dust accretion. Objects the size of 3I-ATLAS provide gravitational seeds that attract surrounding material more efficiently than trying to build planets from scratch through gradual accumulation processes. The chemical composition of 3I-ATLAS offers additional advantages for seeding planetary formation. Its unusual carbon dioxide to water ratio might provide volatile inventories that complement rather than duplicate materials already present in typical protoplanetary disks. This chemical diversity could enhance the range of planetary compositions and atmospheric architectures possible in young stellar systems. Capture of interstellar objects requires precise gravitational dynamics during encounters with stellar systems. Objects must lose sufficient velocity to become gravitationally bound while avoiding direct collision with central stars or ejection through subsequent planetary interactions. The probability of successful capture depends on stellar system architecture, gas disk properties, and encounter geometry. The massive size of 3I-ATLAS increases capture probability compared to smaller interstellar objects. Larger objects experience stronger gravitational focusing effects that enhance interaction cross-sections with stellar systems. Gas drag from protoplanetary disks provides more efficient energy dissipation for massive objects, increasing the likelihood of achieving bound orbits around central stars. Statistical models of interstellar object populations suggest that stellar systems encounter potential seed objects frequently enough to significantly impact planetary formation processes. If interstellar wanderers like 3I-ATLAS occur commonly throughout the galaxy, then most young stellar systems might incorporate external materials during their planet formation epochs. The survival of 3I-ATLAS during billions of years of interstellar travel demonstrates that such objects can maintain structural integrity and chemical composition throughout journeys between stellar systems. This preservation capability ensures that seeding materials retain their original properties when incorporated into new planetary formation environments. Laboratory studies of meteorites show that our solar system incorporated materials from multiple stellar sources during its formation 4.6 billion years ago. Isotopic signatures in primitive meteorites reveal contributions from different types of stellar nucleosynthesis processes, indicating that our planetary system formed from chemically diverse ingredients rather than purely local materials. The seeding hypothesis suggests that planetary formation throughout the galaxy might involve systematic mixing of materials from different stellar environments through interstellar object exchange. This process could create planetary systems with chemical diversity exceeding what individual stellar systems can produce through local planet formation processes alone. Understanding this galactic recycling network requires coordinated observations by multiple space-based observatories. Every major space observatory in human history is simultaneously tracking 3I-ATLAS in the most coordinated scientific investigation ever attempted. The international response to 3I-ATLAS triggered unprecedented cooperation among space agencies, research institutions, and observatory networks that normally compete for limited observing time and resources. Over 30 major telescopes redirected their research programs to focus on this single target, creating the largest coordinated astronomical observation campaign in human history. The coordination began within hours of the initial ATLAS discovery announcement, when the International Astronomical Union issued alerts through the Minor Planet Center's communication network. This system automatically notifies observatories worldwide about newly discovered objects that require follow-up observations to confirm their nature and calculate accurate orbital trajectories. Ground-based observatories from Hawaii to Chile contributed observations using instruments ranging from small survey telescopes to massive mirror arrays exceeding 10 meters in diameter. The Very Large Telescope, Keck Observatory, Subaru Telescope, and Gemini Observatory coordinated observing schedules to provide continuous coverage as 3I-ATLAS moved across the sky from different geographical perspectives. Space-based assets, including the Hubble Space Telescope, James Webb Space Telescope, and Spitzer Space Observatory, before retirement, allocated precious observing time normally reserved for studying distant galaxies and exotic astrophysical phenomena. These facilities provide capabilities unavailable to ground-based instruments, including ultraviolet spectroscopy and infrared imaging at wavelengths blocked by Earth's atmosphere. The European Space Agency's Gaia mission, designed to map stellar positions throughout our galaxy, provided precise astrometric measurements of 3I-ATLAS position and motion. This data enables accurate trajectory calculations and helps determine the object's origin within the galactic coordinate system. Gaia's unprecedented measurement precision allows detection of subtle gravitational perturbations that reveal information about internal mass distribution. Mars orbiters, including NASA's Mars Reconnaissance Orbiter, Europe's Mars Express, and the ExoMars Trace Gas Orbiter, received special instructions to observe 3I-ATLAS during its October approach to the Red Planet. Coordinating these observations required complex orbital mechanics calculations to ensure spacecraft pointing accuracy while maintaining primary mission objectives. Deep space missions, including Europa Clipper, JUICE, Lucy, and Psyche, contributed observations from their unique vantage points throughout the solar system. These spacecraft provide viewing angles impossible from Earth or Mars orbit, enabling stereoscopic analysis of 3I-ATLAS structure and composition from multiple perspectives simultaneously. The Swift Observatory, originally designed to detect gamma-ray bursts from distant stellar explosions, redirected its sensitive ultraviolet instruments to analyze gas emissions from 3I-ATLAS. This mission demonstrates the flexibility of modern space observatories to adapt their capabilities for unexpected scientific opportunities. Radio telescopes, including the Very Large Array, ALMA Observatory, and Green Bank telescopes searched for emissions at wavelengths where 3I-ATLAS might produce signals through natural physical processes or potential artificial origins. These facilities provide complementary information about thermal properties and magnetic field interactions invisible to optical instruments. Data sharing protocols established for this campaign required developing new standards for coordinating observations, processing measurements, and distributing results among international research teams. The unprecedented scale of cooperation created logistical challenges in managing telescope scheduling, data transfer, and scientific analysis across multiple institutions and countries. The coordination reveals just how statistically impossible finding objects like 3I-ATLAS should be. Mathematical analysis proves that discovering 3I-ATLAS violates every statistical model of interstellar object populations by margins that approach impossibility. Professional astronomers calculate object discovery rates using power law distributions that predict the relative abundance of different-sized bodies throughout space. These mathematical relationships, confirmed by decades of asteroid and comet surveys within our solar system, show that small objects vastly outnumber large ones, according to predictable ratios. Finding 3I-ATLAS after only 3 interstellar detections breaks these statistical laws. The size distribution of interstellar objects should follow similar patterns to local asteroid and comet populations, with approximately 10 times more objects at each factor of 10 decrease in diameter. Under these assumptions, discovering a 7-mile-wide interstellar visitor like 3I-ATLAS should require first detecting millions of smaller objects in the 100-meter to kilometer size range. Current interstellar object detection capabilities remain biased toward finding larger, brighter targets that reflect sufficient sunlight for ground-based telescopes to identify against stellar backgrounds. However, even accounting for these observational biases, the probability of discovering 3I-ATLAS among the first few interstellar detections approaches statistical impossibility under conventional population models. Independent research groups calculated similar probability estimates using different mathematical approaches and survey simulation methods. Monte Carlo computer models that simulate thousands of potential discovery scenarios consistently show that finding objects the size of 3I-ATLAS should occur less than once per several million interstellar object encounters under random sampling conditions. The rapid succession of interstellar discoveries since 2017 also violates statistical expectations for detection rates. Astronomical surveys operated for decades without confirming any interstellar visitors, then suddenly detected 3 objects within 8 years. This clustering suggests either remarkable coincidence or systematic changes in survey capabilities and techniques. Survey efficiency improvements through machine learning algorithms and automated detection systems increase the probability of finding interstellar objects, but not by factors sufficient to explain the statistical anomalies surrounding 3I-ATLAS. Modern surveys achieve perhaps 10 times better detection rates than previous generations of astronomical instruments, far below the improvement needed to make such discoveries statistically reasonable. The orbital characteristics of 3I-ATLAS compound the statistical problems through additional improbabilities that multiply rather than add to overall detection odds. Objects approaching from random directions in space should show uniform distribution of orbital inclinations, velocities, and approach geometries. 3I-ATLAS clusters near the ecliptic plane with timing that maximizes observational opportunities. Alternative explanations invoke fundamental errors in current understanding of interstellar object population statistics. Perhaps ejection mechanisms from planetary systems preferentially launch large objects rather than small ones, creating size distributions different from solar system analogs. Or gravitational focusing effects might concentrate interstellar visitors in specific regions of space that increase encounter rates. More exotic theories suggest that 3I-ATLAS represents a member of an unusual population of interstellar objects with characteristics different from typical ejected comet and asteroid populations. Objects formed through alternative mechanisms might show size distributions, chemical compositions, and orbital properties that violate expectations based on solar system experience. The statistical analysis extends beyond individual object properties to population-level questions about the abundance and distribution of interstellar wanderers throughout the galaxy. Current estimates suggest approximately 1 interstellar object larger than 100 meters diameter passes through our solar system annually, yet detection remains extremely challenging due to high velocities and faint brightness levels. These statistical impossibilities pale compared to the exotic chemistry revealed through detailed spectroscopic analysis. 3I-ATLAS carries deadly cyanide compounds in concentrations that reveal formation under chemical conditions unknown in our cosmic neighborhood. Ultraviolet spectroscopy from the Swift Observatory detected characteristic emission lines of cyanide molecules in the coma of 3I-ATLAS, adding another layer of chemical mystery to an object already defying conventional understanding of comet composition. Cyanide appears as sharp spectral features at specific ultraviolet wavelengths when molecules get excited by solar radiation and re-emit light at frequencies determined by quantum mechanical energy transitions. The detection required sophisticated analysis techniques to separate cyanide signals from contaminating emissions by other molecules present in the comet's coma. Cyanide produces relatively weak spectral lines compared to major species like carbon dioxide and water vapor, demanding long exposure times with sensitive instruments to achieve sufficient signal-to-noise ratios for confident identification. Cyanide in space environments typically forms through chemical reactions involving carbon and nitrogen under specific temperature and pressure conditions. The presence of cyanide in 3I-ATLAS suggests either formation in regions of its parent protoplanetary disk, where such chemistry occurred naturally, or subsequent processing during billions of years of interstellar travel that created these compounds through alternative reaction pathways. The concentration levels of cyanide relative to other species provide clues about formation history and chemical processing mechanisms. 3I-ATLAS shows cyanide abundances consistent with formation in cold, dense molecular cloud environments where carbon and nitrogen can combine efficiently without interference from competing chemical reactions that occur under different physical conditions. Laboratory studies of cyanide stability under space conditions show that these molecules typically decompose when exposed to ultraviolet radiation or cosmic ray bombardment over timescales much shorter than the age of step 3I-ATLAS. Finding stable cyanide compounds after billion-year interstellar exposure suggests either unusually stable molecular configurations or protection mechanisms that prevented photochemical destruction. Cyanide also appears in the spectra of some solar system comets, but typically at lower concentrations and with different isotopic ratios than observed in 3I-ATLAS. The unusual abundance patterns suggest formation under nitrogen chemistry, conditions different from those in our local planetary formation environment, possibly reflecting different stellar nucleosynthesis histories or protoplanetary disk compositions. The biological significance of cyanide detection adds complexity to discussions about potential habitability, implications of interstellar object chemistry. While cyanide is highly toxic to most Earth-based life forms, it also serves as a building block for more complex organic molecules that could contribute to prebiotic chemistry under appropriate environmental conditions. Alternative formation pathways for cyanide involve high-energy processes like shock chemistry from supernova explosions or stellar collision events that create extreme pressure and temperature conditions capable of driving unusual chemical reactions. 3I-ATLAS might carry chemical signatures of violent astrophysical events that occurred during its formation epoch. The time-variable behavior of cyanide emissions from 3I-ATLAS shows patterns different from other molecular species, suggesting complex chemical processes occurring within the comet nucleus as solar heating progresses. Some molecular species show correlated variations, while others, including cyanide, display independent behavior that indicates distinct source regions or formation mechanisms. Isotopic analysis of cyanide molecules could provide additional constraints on formation conditions and processing history, but such measurements require spectroscopic resolution and sensitivity beyond current observational capabilities. Future observations with more powerful instruments might reveal isotopic signatures that distinguish between different cyanide formation pathways and processing mechanisms. The cyanide detection, combined with other chemical anomalies, points toward the most spectacular finale as 3I-ATLAS approaches its death. 3I-ATLAS will create the largest comet tail in recorded history as it dies in a spectacular display visible across the entire solar system. The massive size and unusual chemistry of 3I-ATLAS combine to produce tail development potential exceeding any comet previously observed by human civilization. Computer models predict that peak gas and dust production during perihelion passage could create tail structures extending over 100 million kilometers into space, rivaling the distance between Earth and the Sun in linear dimensions. Comet tails form through interaction between solar radiation and stellar wind, with gas and dust particles expelled from comet nuclei during solar heating. Radiation pressure from sunlight pushes smaller particles away from the sun, creating the characteristic curved tail structure that always points away from the central star, regardless of comet motion direction. The extreme carbon dioxide production rates, measured in 3I-ATLAS, suggest that perihelion heating will trigger massive gas releases that dwarf typical solar system comet activity. 129 kilograms per second of current carbon dioxide production could increase by factors of 10 or more as solar heating intensifies during closest approach, creating unprecedented volumes of gas for tail formation. The retrograde orbital motion of 3I-ATLAS produces unusual geometry for tail development, compared to typical solar system comets that orbit in the same direction as planetary motion. Retrograde motion creates relative velocities that enhance particle interactions with solar wind, potentially producing tail orientations and morphologies never before observed in detail. Dust particle analysis from early observations shows 3I-ATLAS produces grain sizes and compositions different from typical solar system comets. The unusual surface chemistry might create dust populations with altered optical properties that reflect, scatter, and absorb sunlight differently than normal comet dust, potentially producing tail colors and brightness levels unlike previous comet displays. The 7-mile diameter nucleus provides enormous surface area and internal volume for gas and dust production compared to smaller comets that typically develop prominent tails during solar approaches. Surface-to-volume scaling relationships suggest that 3I-ATLAS could maintain high activity levels throughout its perihelion passage, rather than experiencing rapid depletion of volatile materials. Multiple tail structures might develop simultaneously as different chemical species respond to solar heating and radiation pressure through distinct physical mechanisms. Carbon dioxide, water vapor, dust particles of various sizes, and potentially metallic vapors could create separate tail components with different orientations, colors, and temporal evolution patterns. Ground-based observers in both hemispheres might achieve naked eye visibility of the 3I-ATLAS tail system during post-perihelion emergence from solar conjunction in December 2025. The tail could potentially become one of the most spectacular astronomical displays visible from Earth, comparable to historically bright comets that captured public attention and cultural significance. Space-based observatories will document tail development and evolution with unprecedented detail through coordinated observations across multiple wavelength ranges. Ultraviolet imaging reveals gas compositions and ionization states, while infrared measurements map dust temperatures and size distributions throughout the tail structure. The death throes of 3I-ATLAS during perihelion passage might trigger explosive fragmentation events that create multiple tail systems from separate nucleus fragments. Such breakup events occasionally occur when internal pressure from sublimating gases overcomes gravitational binding forces, creating spectacular displays as multiple objects develop independent tails. Observations of this unprecedented display will establish protocols for studying the hundreds of additional interstellar visitors that future surveys will discover. Advanced survey telescopes will transform interstellar object detection from rare accidents into routine discoveries that catalog hundreds of cosmic visitors annually. The Vera C. Rubin Observatory, beginning full science operations in late 2025, will revolutionize interstellar object detection through systematic sky surveys that image the entire southern hemisphere every few nights with unprecedented sensitivity and automation. This facility alone could discover 6 to 51 additional interstellar objects over the next decade, according to statistical projections based on current population models. The 8.4-meter primary mirror of the Rubin Observatory collects light from sky areas equivalent to 40 full moons simultaneously, creating survey capabilities that dwarf previous astronomical instruments. Advanced CCD cameras produce images containing over 3 billion pixels, requiring machine learning algorithms to process the enormous data volumes and identify moving objects against stellar backgrounds. Automated detection systems developed for the Rubin Observatory use artificial intelligence trained on millions of astronomical images to distinguish genuine moving objects from instrumental artifacts, cosmic ray hits, and other false positive signals. These algorithms achieve detection efficiencies exceeding human visual inspection, while processing data volumes impossible to analyze manually. International coordination among multiple survey facilities will create global networks capable of tracking interstellar objects continuously across the sky as Earth rotation and orbital motion change viewing perspectives. The European Space Agency's Euclid mission, NASA's Nancy Grace Roman Space Telescope, and ground-based facilities worldwide will contribute complementary observations. Next-generation surveys will detect interstellar objects at greater distances and earlier in their solar system passages, providing extended observation periods for detailed characterization before objects fade beyond detection limits. Earlier detection enables coordinated observations by multiple facilities and potentially spacecraft missions designed to intercept particularly interesting targets. Statistical models predict that systematic surveys will reveal size distributions, compositional diversity, and population characteristics of interstellar objects that remain hidden when detection depends on chance encounters with objects passing close to Earth. Large statistical samples will enable population studies that distinguish between different ejection mechanisms and source stellar systems. The discovery rate projections suggest approximately 1 to 2 interstellar objects per year achievable with current survey technologies, increasing to potentially dozens annually as detector sensitivity and survey strategies improve. This transformation from rare events to routine discoveries will fundamentally change how astronomers approach interstellar object research. Future space missions, specifically designed for interstellar object encounters, could become feasible once surveys provide sufficient target catalogs and trajectory predictions. The European Space Agency's Comet Interceptor mission demonstrates proof of concept for rapid response spacecraft that could intercept newly discovered objects during their solar system passages. Advanced spectroscopic capabilities on future survey telescopes will enable chemical characterization of interstellar objects during initial discovery observations, rather than requiring extensive follow-up campaigns. Time-domain spectroscopy could reveal chemical evolution and activity patterns throughout entire solar system, passages with temporal resolution impossible for individual objects studied today. Machine learning applications will expand beyond simple detection to automated classification systems that identify unusual objects requiring priority follow-up observations. Algorithms could flag potential interstellar visitors based on orbital characteristics, chemical signatures, or other properties that distinguish them from solar system objects. The data processing challenges for next-generation surveys require developing new computational architectures and storage systems capable of handling petabyte-scale databases with real-time analysis requirements. Cloud computing resources and distributed processing networks will enable rapid response to time-critical discoveries. These routine discoveries will reveal that interstellar wanderers represent the most abundant objects in the galaxy. Interstellar objects like 3I-ATLAS might represent the most common type of matter in the Milky Way, outnumbering stars by ratios that dwarf every previous estimate. Recent theoretical calculations suggest that stellar systems throughout the galaxy eject far more planetary building materials into interstellar space than previously imagined, creating populations of wandering objects that exceed stellar abundances by factors of millions to billions. 3I-ATLAS might represent a typical member of this vast cosmic diaspora, rather than an unusual exception. Computer simulations of planetary system formation show that gravitational interactions during planet assembly naturally eject substantial fractions of available solid materials into interstellar orbits. Giant planet migration, stellar encounters, and orbital instabilities create ejection rates that remove 10 to 90% of original planetary building materials from their parent stellar systems. The ejection efficiency depends on stellar system architecture, with systems containing multiple giant planets showing higher ejection rates than simpler configurations. Binary star systems produce even more extreme ejection through three-body gravitational interactions that can scatter entire planetary systems into interstellar space during close stellar encounters. Scaling these ejection rates across the approximately 400 billion stars in our galaxy produces estimates of interstellar object populations that stagger the imagination. Conservative calculations suggest over 10 to the 18th power individual objects larger than 1 kilometer diameter currently wander between stars throughout the Milky Way, creating number densities that exceed stellar populations by astronomical margins. The mass contained in interstellar objects might rival the total mass in all stellar systems combined, when accounting for size distributions that include objects ranging from asteroid dimensions to potential rogue planets ejected intact from their formation environments. This interstellar matter represents a previously unrecognized component of galactic mass budgets. Detection bias severely limits current observational access to these populations because interstellar objects appear bright enough for discovery only during brief passages through stellar systems with sufficient illumination for ground-based telescopes. The vast majority of interstellar wanderers remain invisible in the darkness between stars, creating a hidden universe of objects that occasionally become accessible through chance encounters. The chemical diversity implied by such enormous populations suggests that interstellar objects carry samples from virtually every type of stellar system and planetary formation environment throughout galactic history. Different stellar masses, metallicities, ages, and formation epochs contribute to chemical signatures that span the complete range of cosmic element production and processing mechanisms. Understanding interstellar object populations requires developing new theoretical frameworks for galactic evolution that account for continuous matter exchange between stellar systems through ejection and occasional capture processes. This cosmic recycling network might play crucial roles in distributing materials and potentially biological compounds throughout the galaxy over billion-year timescales. The survival statistics for billion-year interstellar journeys determine what fraction of ejected materials remains structurally intact and chemically recognizable when encountering new stellar systems. Objects like 3I-ATLAS demonstrate that substantial preservation is possible, suggesting that ancient materials circulate throughout the galaxy as cosmic time capsules. Radio astronomy searches for interstellar objects using thermal emission detection could potentially catalog populations invisible to optical surveys by detecting objects in the cold darkness between stars. Such surveys would require unprecedented sensitivity and survey strategies adapted to the unique observational challenges of detecting faint thermal sources against cosmic background radiation. The implications transform our understanding of how chemical elements and potentially life itself might spread throughout the cosmos. 3I-ATLAS proves that our solar system represents a chemical anomaly in a galaxy where most planetary formation follows completely different rules. The extreme chemical signatures observed in 3I-ATLAS indicate that water-rich, carbon-poor planetary systems like ours occur rarely throughout galactic history, while carbon dioxide-dominated environments might represent typical conditions for planetary formation around most stellar types. This revelation inverts fundamental assumptions about cosmic chemistry and the prevalence of Earth-like worlds. Stellar nucleosynthesis processes, operating throughout the 13.8 billion-year history of our universe, created systematic variations in elemental abundances that depend on stellar mass, formation epoch, and galactic environment. Stars formed during different periods produced planets with chemical inventories, spanning ranges far exceeding the narrow conditions that characterize our local solar neighborhood. The metallicity differences between thick disk and thin disk stellar populations demonstrate that planetary formation chemistry evolved dramatically as the galaxy aged and successive generations of stars enriched interstellar space with heavy elements. 3I-ATLAS carries chemical signatures from epochs when stellar nucleosynthesis operated under conditions absent in present-day galactic environments. Laboratory analysis of meteorites from our solar system reveals isotopic ratios and elemental abundances that cluster within narrow ranges compared to the diversity implied by galactic chemical evolution models. Our planetary system apparently formed from unusually homogeneous materials compared to the chemical chaos that characterizes most stellar formation environments throughout cosmic history. The carbon dioxide to water ratio of 8:1, measured in 3I-ATLAS, might represent typical volatile inventories for planetary systems formed around stars with different masses, ages, or chemical compositions than our Sunday. Such environments could produce terrestrial planets with atmospheric chemistry fundamentally different from Earth's nitrogen-oxygen atmosphere. Habitability assessments for exoplanets typically assume water-based biochemistry operating under chemical conditions similar to Earth's environment. 3I-ATLAS suggests that alternative biochemistries based on carbon dioxide, methane, or other chemical foundations might dominate throughout the galaxy, expanding the potential range of biological processes beyond Earth-based analogies. The preservation of exotic chemistry in 3I-ATLAS over billion-year timescales demonstrates that alternative chemical architectures remain stable under space environmental conditions, suggesting that unusual planetary chemistry could persist throughout geological and astronomical time periods. Such stability expands the potential for discovering chemical signatures of alternative biochemistry in exoplanet atmospheric observations. Future astronomical surveys of exoplanet atmospheres using next-generation space telescopes might reveal that Earth-like chemical compositions represent rare exceptions rather than typical examples of planetary chemistry. The James Webb Space Telescope and subsequent facilities could detect atmospheric signatures consistent with the carbon dioxide-dominated chemistry observed in 3I-ATLAS. Understanding the true diversity of planetary chemistry throughout the galaxy requires moving beyond solar system experience to embrace the full range of chemical possibilities demonstrated by interstellar visitors like 3I-ATLAS. These objects provide direct access to materials formed under conditions impossible to study through solar system samples alone. The implications extend to astrobiology and the search for life throughout the cosmos. If most planetary systems develop chemical architectures different from Earth's environment, then biological processes might follow pathways unknown to terrestrial biology, operating through chemical mechanisms adapted to carbon dioxide-rich atmospheres and exotic volatile inventories. 3I-ATLAS represents more than an unusual interstellar visitor. This ancient wanderer carries revolutionary evidence that our understanding of cosmic chemistry, planetary formation, and the potential for life throughout the universe requires fundamental revision based on chemical diversity far exceeding previous imagination. The successful detection, characterization, and scientific analysis of 3I-ATLAS establishes humanity's capability to intercept and study these fleeting cosmic messengers, opening unprecedented opportunities for exploring the chemical evolution of our galaxy through direct observation of materials formed under conditions spanning billions of years of cosmic history. As 3I-ATLAS continues its eternal journey into the darkness beyond our solar system, it leaves behind transformed scientific understanding and establishes new paradigms for studying the vast population of interstellar wanderers that carry the chemical heritage of our galaxy through the cosmic void between stars.